Hello everyone, welcome again to my channel. So today we'll discuss one problem from Leetcode, that is 323, number of connected components in an undirected graph. So the problem statement is saying you will be given with n number of nodes, they are labeled from 0 to n minus 1, and you will be given with a list of undirected edges. You have to find like how many connected components are present. What that means is here n equal to 5 means n number of nodes are given and you have a list of edges. One edge means they will be point from one node to another node. So now if you look here 0 to 1, one edge is present, 1 to 2, one edge is present. That means 0, 1, 2 are connected and 3 and 4 is connected. So 3 to 4, one edge is there. So together if you see here two components we can found. One is 0, 1, 2 together, another was is 3 and 4. So the answer will be 2. If by chance one another edge is present, that is 2 comma 3, then 2 to 3 one connection will be there, then together it will form only one single component. So that time the answer will be 1. So how to find this we have to see next.
So how to solve this problem? So as it's a graph problem, so we can use DFS or BFS technique to solve this problem. Let's take DFS for example. Now first thing what we have to do is we have to form an adjacency list from this input. So if you form an adjacency list from this input, the input will be like this. For 0, 1 edge is only present a node, and for 1, 0 and 2 is connected, for 2, 1 is connected, for 3, 4 is connected, and for 4, 3 is connected. Now we can imagine a graph shape like this, like 0, 1, 2 is connected and 3 and 4. So our job is to find like how many connected components are there. Obviously this adjacency list is presenting a graph, but that is the pictorial view. We have to find now like how many components are there. So for this purpose, as we are doing a DFS traversal, we can maintain a visited array. This is a Boolean array where it will be said like this particular node is visited or not. And the length of this visited array will be same as the number of nodes. Now for DFS technique, what we can do is for each and every node we can go and do a DFS. So suppose we have like 5 nodes, so 0, 1, 2 and 3 and 4. So for node 0 we have to start the DFS technique. So it will be start from here. So node 0 we will mark it as visited. Here also in this array also we will mark it as visited. Then node 1 it will take as per the DFS rule, because 0th neighbor is 1, and 1 will be also get visited. Then from 1 it can again go to the depth of 2 and 2 will be marked as visited. But it can't move further, right? Because there is no other nodes present and there is no other adjacent nodes for 1 also. So one DFS run is completed and we can see that 3 nodes are visited. So after one successful DFS run, we can increase our count to 1. Then we have to check for 1. Like from 1, if we start the DFS, what will be the result? But before that, we have to check it is visited or not. For 1, when we will check for DFS, it is already visited. So we can't start a DFS from here. For 2, same case, we can't start a DFS from here. Now for 3, if we want to start a DFS, it is possible because 3 is not visited. So we will mark it as visited and we can start a DFS run. Then for 3 after that it will go to 4 and 4 we will mark it as visited. So another DFS run is completed. So we will make a +1 here. Now for 4. So because for 3 it is completed. Now for 4 if we check, 4 is already visited, so we can't start a DFS run from here. So altogether total 2 DFS actually completed. So the answer will be 2. So this is the way we can find the number of components using DFS technique. But what is the time complexity in this case? So each and every DFS will take almost O of B plus E time, right? So where B is the number of vertices and E is the number of edges. And as it is, we are doing it for like n number of nodes, right? So for worst case scenario, if all are not connected, then they will be all individual, right? So it will take almost O plus BE into B time. So this will be the time complexity. Now we will see another technique by using union and find. Okay, how we can reduce the time. Now we'll see by using union and find technique how we can reduce the time. Union and find is a concept from disjoint set data structure. So if you don't know also, that's fine. There is no prerequisite that we have to know that thing. While processing, we can get to know these things. I will explain everything. So what we can do in this case is, the first edge we got as 0 and 1. So 0 is a node and 1 is a node, right? So we have to mark them. But before that, we have to write somewhere what are the number of nodes present. That is 5, total number of nodes. So now I will mark 0 and 1, means write somewhere. To do a union and find, we need help of two kind of array. One is parent array and another is rank array. What is that? I will explain now. Parent means for a node, who is the parent of that node? Means which node it is following. That will be the parent of that node. And it will be given as a rank. Initially, for each and every node, the parent will be that node itself. Means for 0, the parent will be 0, for 1 it is 1, for 2 it is 2, and 3 and 4. And all their rank will be 0. So initially we have to fill with that thing. So it will be 0, then 1, then 2, then 3, then 4. And all of them will be 0. Now, before proceeding, we have to know few rules here. One is, if parent for both are same, do nothing. If rank for both are same, second will follow first and second's parent will be first. And first rank will be first rank plus 1. If rank of I greater than equal to rank of j, parent of j will be I. So while proceeding, we will see these rules and it will be more clear. So first, for 0 and 1, who is the parent? For 0, the parent is 0, and for 1, the parent is 1, right? And they are not same, means both of their parent is not same. Now we'll check what are their rank. For 0, the rank is 0, and for 1, the rank is also 0. So here if you check the rule, if rank for both are same, second will follow the first. Means if both of their rank is same, let's assume the second one will follow the first one. When it is following the first one, that means one's parent is now 0. So here what we can update is parent of 1 will become 0 now. And as 1 is following 0, that means 0's rank will be increased. He will be very happy, right? So 0's rank will be now increased by 1. So 0's rank will be become 1 now. Now we have to go for the second one. For second one, what we can see is two nodes are present. One is 1 and one is 2. We have to find for 1 who is the parent. For 1 the parent is 0. And for 2 who is the parent? For 2 the parent is 2 itself. So now we have to check what are their corresponding ranks. For 1 the parent is 0. For 0 the rank is 1. Right. That means for 1 the rank is 1. And for 2 the parent is 2, and for parent 2 the rank is 0. So rank of 2 is 0. Now whose rank is more? 1's rank is more. That means 2 will follow 1. So here if 2 is there, then we have to make an arrow this side, like 2 will follow 1. And we know that the rank of 0 is 1. So now 2 will follow 1. And as 2 is following 1, then who is 2's parent? 2's parent is 1, but who is 1's parent? That is 0. So ultimately 2's parent will be also 0. So we have to update here 2's parent as 0. Now before proceeding, one thing what you can notice from here is our main goal is to maintain it as a set, like who are in the same component, they should follow one leader only. For 1, 0 is become the leader. For 2 also, as 2 is following 1, 1 is following 0. So 2's actually parent is 0. You can imagine it as a train. So if you ask, suppose 0 is the engine and 1 and 2 are the cells. So for 1, who is the engine? 0. For 2 also the engine is 0 because they are from same family, right? Now for 3 and 4. For 3 and 4 we have to check for their rank. For 3, who is the parent? 3. And the rank of 3 is 0. So rank for 3 is 0. For 4 the parent is 4 and rank is 0. So both of their rank is 0. So as both of their rank is 0, that time what we can do? Second can follow the first one. So as 3 and 4 is present, so as both of their rank is same, so you just imagine that 4 will follow 3 and 3's rank will be increased to 1 and 4's new parent will be 3. So we can, for 4, the parent will become 3 and rank of 3 will be increased to 1. And every time when we were doing this operation, that time we have to reduce this number. Totally initially 5 nodes are present. So when we did the first operation, that time we have to reduce it to 4. For second operation we have to reduce it to 3. And for the third operation we have to reduce it to 2. And that time whatever will be the result, that will be your answer. So initially from the input, actually this 3 was the input. This 3 and 1 and 2 and 0 I have added for understanding purpose. So initially we imagine like this is the input where 3 edges are present. So that time what is the answer you are getting is 2. That is the correct answer. Now I have taken 2 more edges, 3 and 1 and 2 and 0, to understand it more. So let me erase few things here and again proceed. Now for edge 3 and 1. 3 and 1 we have to find the ranks. For 3 what is the rank? For 3 who is the parent? 3 itself. And what is the rank for that? That is 1. For 1 what is the parent? For 1's parent is 0. And what is the rank of 0? That is 1. So both of their rank is now 1. So then who will follow whom? 1 have to follow 3. Because second one will follow first one. As 1 is following 3, then what will happen? 3's rank will increase. So it will become 2 now. We have to update the same thing here also. So we can erase this part and then 3's rank we have to increase to 2 and 1's parent will be now 3. So 1's parent will become 3 and the rank of 3 will become 2. And we have to reduce it to 1. Now if you check till here, are we getting the correct result? Yes. As 3 and 1 is now connected, then these two separate components have become a single component now. So the answer is 1. That is correct. Now check for the last one, that is 2, 0. For 2, 0, for this edge we have to find their ranks. For 2, who is the parent? For 2 the parent is 0. For 0, who is the parent? That is also 0. But here is one rule. If parent for both are same, do nothing. Why it is? Because if you check from the actual graph also, 2 to 0, if you try to form one edge, then what will happen? It will just form a loop. And loop, which edge will contribute as a loop, that we will not consider. Because that is anyhow will not help us to determine a component. Because if they are somehow connected, that will be our answer. if it is forming a loop, that is not anyhow helping us, right? So we have to discard that. So if there is any other edge which is trying to form a loop, that this algorithm only will discard. So we don't have to take care of that. And that time the count will not be reduced, right? So this is all about the union find technique. So if you look at carefully, our job is to, so let me remove this one. So our job is to point each and every portion to ultimate absolute parent, and if they are following that, that means from there we can determine how many components are there. And this technique is almost linear, right? So every time we are just finding the parent and rank, and we are completing the number of pages which is given to us. If we traverse all of them, then we will get the result. So in almost linear time we are solving this problem. Now we'll see the code. Now we'll discuss code for both DFS technique and using union and find technique. So here first one is the DFS technique. So I have defined one graph here at a static class. Then in the main method I am just passing these edges and the count. Okay. So in the count component method I have created the graph object, and there I am passing the edges. So edges I have taken twice, like from 1 to 0 and 0 to 1. That is considered as 2 edge because it is a undirected graph. Then I am keeping one counter as count equal to 0, and I am assign like initializing one boolean visited array field. And then if that node is not visited, and I am doing a DFS. So if it is not visited, that time I am doing a count plus plus, because that will be a successful DFS. So and here is the DFS recursive code. So at the end, whatever will be the result of count, that I am returning as a result. So here if you check 0, 1, 1, 2, 3, 4 was the edges. So the output we are getting as 2. So means 2 components are there. Now the another technique is using union and find. So here we need 3 things, right? Like one is the parent array, and one is the rank array, and group means the number of nodes which we have to reduce to get the result. So here is the main method, we are passing everything, and in the count component method we have defined the parent, rank, and the group. Parent array will be have length as n, same for rank also, and the group will be initialized as n. Then initializing parent as that index number itself, because initially every parent, for every node the parent will be that node itself. Then for each and every edges we are trying to find who is the parent and who is the rank, and based on that we have to take some decision. So union means we have to find like their parent first, right? So for I and j, whatever value we are getting, if you see in the video, so for them I am trying to find their parent. So it is calling this find method, so where I am checking who is the parent for this particular node. So if that node itself is not the parent, then it is going to search like who is the parent next. So ultimately if the index and the value is same, then that will be the parent, right? So for a while loop I am checking the same thing. For p of j also we are doing the same thing. If both of their parent is same, that means it will create a loop. That's why we are just returning, we are doing nothing. If it is not the case, then we are checking if rank of pi is greater than rank of pj. That means for parent of pj will become pi, right? Means if I have the higher rank, then another node have to follow me, and I will become parent of him. Same case for if rank of pi less than rank of pj, then just the reverse thing. But if both of their rank is same, that time what you have to do is just the second one will follow the first one, and for first the rank will increase to +1, right? So parent of pj equal to p of I, rank of pi will be a plus plus, and every time we have to do a group minus minus. If it is a successful thing, then we have to do a group minus minus. Only case when it will be not a minus minus, if it is containing a loop, means that time that edge we will not consider. and at the end we will get the result. So let's run it from here. So here I have inserted another edge called 3 comma 1, which will connect both of the component, not like the previous use case. And here I think the output will be 1. Let's check. Yeah, so here the result is 1 because the edge 3 and 1 is connecting both of them. If we remove it, then we will get the 2 components. Yeah, this time it is the 2 components we are getting. So this is all about the coding for both the techniques. If you submit this in Leetcode, you can see for the union find technique, the runtime is less. Thanks for watching.